Thank you. We had 2 lectures on this last week. We saw the definition of the partial derivative. We saw the principle of how we obtain partial derivatives by using all the results about differentiation we have from single variable case. And the main key idea was this principle in bold here, back a few pages, which is when you're differentiating with respect to one variable in a multivariable function, you treat the other variables for that purpose as if they were constants, and then just apply the normal rules of differentiation that you have. We look briefly at the graphical interpretation of them to do with cross sections through the surface, well, at least for functions of 2 variables. We'll come back to that today and look at a bit more of the graphical interpretation we can give to them. And I did say this last time, but just to emphasize it, I mean, the approach we're outlining, although we're mainly concentrating on functions of 2 variables, it does indeed carry through to functions of any number of variables. So there's this example here, example 1.4. Turn this thing on, sorry. Turn it on. And the light, you see that? It'll click in a minute. So example 1.4 on page 5, we have this function g. So it's just to emphasize the point that the same principle carries through. So here's a function of 3 variables, just a kind of single polynomial term in them, if you like. It's the same. X squared y to the power of 4 times z cubed. So this has 3 partial derivatives, 3 first-order partial derivatives. First-order partial derivatives, and they are, of course, dg dx. Because it's a sorry, this is x y z. So no, that one. Yeah, because it's a function of the 3 variables x, y, z. That's a misprint in the notes. Yeah, so correct that in the notes. So sorry, yeah, when it's written in the notes, it's got x, y, x. So it should be x, y, z. There should be x, y, z. Thank you. So this is these 3 partial derivatives. So you just apply that principle. When you're differentiating with respect to one variable, the other variables are held constant. So when you look at this and looking for its x derivative, the y and z you think is constant. So then what you're seeing is just a constant times x squared. And so the derivative of that will just be 2x times whatever the constant was. And you leave the constant unchanged if it should be there still as the factor in the derivative. Similarly for the y derivative, what we see is, okay, a constant, x squared times z squared. It has a funny form, but it's nevertheless a constant for this purposes. Constant multiplied by y to the power of 4. So that's going to have the derivative 4 times y cubed times the constant value that was there. And finally, dg dz will be 3 x squared y to the power of 4 z squared. Okay. Now that example is fairly straightforward. It's just a single polynomial term. But, you know, just take care and carefully apply methods like, so for more complex functions, you're going to have to use the linearity of the differentiation process, the product rule, the quotient rule, the chain rule, importantly, when you've got functions of functions, complex functions built up using composition. All the, you could just keep listing here all the techniques of differentiation that we had, logarithmic differentiation, standard functions, or derivatives of standard functions. All the stuff you know about differentiation already, combined with that principle of how you handle functions where there's more than one variable. Okay. Okay. Any questions on that or points on that? Good morning. So then we come to section 1.6, which adds a bit more to the graphical interpretation business about thinking geometrically what these partial derivatives signify and mean. So we're going to look here at, let's go back to the notes, we'll click off that page. I'll scan it. Where are you in it? I mean, I'll put the scans up of it. All right, okay. But they'll go up on Moodle afterwards anyway. So coming to section 1.6. So here, this is talking about the tangent plane to a surface. Okay. So just as a function of a single variable, possesses tangent lines to the graph of that function, we've seen already that a function of two variables the equivalent thing to the graph of the function is the surface defined by the function. Okay, we looked at that in the first lecture, and there's a little sketch of one back here. So function x times an exponential. So the xy plane is the ground bottom plane there. Z is the vertical axis. And so at any point on the ground plane, the function z equals f of xy, whatever it is, that gives you a height. And as that varies continuously around the ground plane, it describes a surface lying over the plane. Over the plane for positive heights and under the ground plane for negative heights. And so if you imagine a point on such a surface, rather than having a tangent line, because of the step up in the dimensions, from like a curve of a function of a single variable to now we're talking about a surface of a function of two variables, the corresponding thing to a tangent line from the one variable case is now a tangent plane. Okay. So at any point on the surface, if the surface is continuous and smooth, so it has partial derivatives, you should be able to get a nice description of what the tangent plane lying over that surface is. Okay. So this is the plane, which is tangent to the surface, and the slope of the plane in any direction corresponds to the rate of increase or decrease or whatever of the function in the corresponding direction. So we got some material here in the notes about this. So we're dealing with the function z equals fxy. And we're going to think of this point P on the surface. Now I'll try and implement this on the computer in a moment for you. So we've got a point P on the surface. And so we're going to let the coordinates of the point on the surface be xp, yp, zp. Okay? So in particular, this point P, the z-coordinate zp will be equal to the function f of xp, yp. Yeah? So you've got the x, y, and z axis. You've got the surface lying over the plane somehow. There's this point P on it. The coordinates xp and yp are down here on the ground plane. And this value here is ZP, which is the height of the point above the surface. Height of the point on the surface above the ground plane. So the surface, you think, is some undulating sheet above the ground. And so we're focusing our attention on P here. And what we want to obtain is some kind of description that gets harder and harder to draw neatly by hand, but some kind of description of the tangent plane to the surface at that point P. Okay, so this is going to be the tangent plane T, it's called in the notes. And we can describe this tangent plane using the partial derivatives, as it discusses in the notes.
What is T represents?
T is the plane.
For that squiggly plane.
Now the black portion there is the surface. So this is the surface defined by z equals fxy in black. T is the tangent plane, which we're going to build a description of now. Sorry? Yeah, but the surface is defined by this function, the z equals fxy. So the height over any point xy is given by the function f. That's how the surface is defined. Yeah. Now, any plane, as it says in the notes, the plane T has an equation z, and we can think of this as alpha x plus beta y plus gamma. Okay, so any plane in 3 dimensions can be described by an equation of this form, and the thing on the right is just the general linear expression in x and y. So a constant times x plus a constant times y plus another constant, gamma. Okay, these are alpha, beta, and gamma are real constants. Okay, so any plane can be described like this. So we want to, in order to describe T, we'll have to give a concrete description of alpha, beta, and gamma. Okay. And that's what's given in the notes there. Okay, I'll just switch over to the. Let's give you a minute to get that, and I'll switch back to the notes.
What kind of question are we going to get related to this?
Well, there's an example afterwards, example 1.5, that we could ask. So it could be given a certain function, find the description of the tangent plane at a certain point. Switch back to the notes. So if we look at the coefficients alpha and beta first, well, this is the tangent plane to the surface. Alpha and beta are the gradients of the tangent plane. Okay. So if you take the equation of the plane and differentiate it with respect to x or y, well, if you differentiate it with respect to x, you get the quantity alpha. dz dx will just be alpha. If you differentiate it with respect to y, you get beta. dz dy is beta. So alpha and beta are the gradients of the tangent plane in the x and y directions. Now, but this is the tangent plane to the surface. So those gradients of the tangent plane have to be, or are by definition, the same as the gradients of the surface in those 2 directions. Okay? So that means that's summarized in equations 1.27 and 1.28 here. Alpha, which is dz dx, that's going to be the same as the derivative of the function f in the direction x. Okay? So we're talking about the tangent plane, the one that captures the rate of change of the surface, the height of the surface. Similarly, beta is going to be df dy, and both of those derivatives of f evaluated at the base point we're talking about, so at the coordinates xp, yp. So that tells us how to describe the alpha and the beta in terms of the surface, in terms of the function f defining the surface. Okay, so in this kind of setup, we consider that we already know the function f. We're dealing with a given base point. Okay, so we know f, we know xp and yp. Using that information, then we can calculate alpha and beta. So the only thing left to determine in the equation for the plane then is the constant gamma. But the tangent plane touches the surface at the base point P, which we described. Okay. So the height of the surface above the coordinates xp, yp, so it's the value of the function f of xp, yp, that's going to be the same as the z coordinate you get from the equation of the plane when you put the base points into the equation of the plane. Okay. So this height zp, it should come about both from evaluating f at the base point, here on the right, f of xp, yp, and also from evaluating the equation of the plane at the base point. So alpha xp plus beta yp plus gamma. Okay. So we've got f of xp, yp on the right-hand side, and we've got alpha xp plus beta yp plus gamma on the left-hand side. So we just move the stuff around, and we end up with gamma is the value of the function at this point. That's the height of the point P, minus this combination of alpha and beta, which are the two derivatives of the function evaluated at the base point xp, yp, multiplied by the corresponding coordinate. Okay. Okay, so we'll work through this example, example 1.5. So this is describe the tangent plane to the surface given by, so the surface is given by this z equals f of xy, and the function we're talking about here is given in the problem x squared y plus 2y squared plus x plus 1, the polynomial function. It's nonlinear. It's got order 2. It's got order 3. In fact, it's got x squared times y. So it won't just be a plane itself. It will be some kind of curved surface. And we need a base point. So describe the tangent plane to the surface given by this at the base point. And we're just given the x and y coordinates here. So that's our, let's call that xp, yp to coincide with the description given earlier. Okay. So the solution, well, it's given in the notes, but I'll just kind of write a little bit just to talk through it. So the tangent plane has equation, as all planes do, in 3 dimensions, z equals alpha x plus beta y plus gamma. And we describe now how you obtain alpha, beta, and gamma from the function f and the base point information. So alpha is df dx evaluated at xp, yp. So df dx is 2xy plus 1. Actually, there's a misprint in the notes here. You can see in equation 1.33. Equation 1.33 in the printed notes, I omitted that plus 1. I didn't do the differentiation correctly when I was typing it. So alpha is this derivative evaluated at the base point xp, yp. So xp is 2, yp is 3. If we put those in, So it's going to be 13. So when you put in these values for xp and yp, you come out with 13. So alpha is 13. We can determine the coefficient alpha. Similarly, beta would be df dy, again evaluated at the base point xp, yp. So df dy here, remember we're differentiating with respect to y, so we think of the x as a fixed constant. So we're just going to get x squared plus 4y. The x differentiates to 0, as does the 1, because we're differentiating with respect to y. So those are just treated as constants. And that should be evaluated at the base point xp, yp. That's what I mean by those subscripts. So we have x is 2, so we've got 4 here. 4 plus 12, isn't it? Yeah, 16. So finally, the gamma, which is the constant coefficient from the equation of the plane. Well, according to the notes, this was f at xp, yp minus alpha xp minus beta yp, isn't it? So we have all that information now. We can just plug all of that in. When you put in 2, 3 into the original function f, you've got 12 here, 12 plus 2 times 9, 12 plus 18, so you've got 30, 32, 33. Check my arithmetic as we go. So 33 is should be the height of the function above the base point. And then we've got minus 2 times 13 minus 3 times 16. So it's 33 minus 26 minus 48, just whatever it is. Minus 41, yeah. So that seems to be our gamma. So the alpha, beta, and gamma, the beta is correct, but the alpha and gamma are incorrect in the notes because of my mistake with the differentiation up here. So we can say finally that so the tangent plane to this surface at the base point xp, yp, which is 2, 3, is given by this equation. Z is 13x plus 16y minus 41. Sorry? Yeah, all these pages get scanned in. Is any questions about that, or any comments about that at all, or things you'd like clarified on it?
What you've written down, all the maths.
Sorry?
What you've written down, all the maths.
I think so. Yeah. Yeah, you need the explanation pieces in these. Yeah. The equations on their own don't tell the story. You need the kind of explanations in between. Yeah. Yes, question? Okay, shh, we got a question here. Yeah. Which equations? I don't think they are explicitly given. But the way you should, I think if you're searching for the equation for a plane, well, see, the problem is there are many different equivalent ways of giving equations for a plane. Sometimes I think what might be in the formula booklet is this kind of thing. A plane in R3 has the equation, although it mightn't even be given, but it's probably given something like this, which is ax plus by plus cz plus d equals 0, something like that. Now that's just a different but equivalent presentation of what we've given already. Because to get the expression that I was using, you just divide across by c to get that. Because then you'd end up with z equals something x plus something y plus a constant. Another way to remember it is to put a comment that this thing is the general form of a linear function of x and y. So if somebody tells you, what's the possibilities for a linear function of x and y, it has to be something of this form, okay? Because all you're allowed is just some constant multiplied by x plus a constant multiplied by y and maybe another constant. If you do anything else to the x's and y's, if you multiply them together or raise them to a power, that's non-linear behavior, okay? So the function kind of has to appear like that. But I'd expect people to know what the equation of a plane would look like in 3 dimensions. I think that's so to know this kind of thing. But the formula booklet is up on the Moodle area, so you can see everything that is there. Yeah. Okay, so now I only showed you this briefly the other day. Let's get back to the notes. And I put a link to it in the Google Plus page in a comment to the first lecture's lecture recording. But it's a little demonstration It's a demonstration of the graphical interpretation of these partial derivatives. Now this is done in Sage, but it's certainly something that you could reconstruct in MATLAB as well, yourselves. So I specified the function. I've got a program here that plots the function and also plots 2 cross-sections of the surface. Okay, so the green and red there are cross-sections of the surface, so where one of the variables is held constant and the other variable is changed, and so that describes then a parametric curve in 3 dimensions which is following the surface. It's a cross-section of the surface. Okay, so the red one is going in it's going at a fixed value of y, so it's going parallel to the x-axis, and the green one is going parallel to the y-axis at a fixed value of x. And in the graphs underneath, I've straightened these out. Now they're not doing anything interesting at the moment because they're both just flat. But when you change the base point, so this a and b is the coordinates of the base point. You can see they look a bit more interesting. The base point is at the intersection, and so these are the 2 cross-sectional curves which are going through there, and the little widget shows you them straightened out. So we could try and add to this, try and add in to visualize the tangent plane at that particular point. You see, there's a place in the code here. You can do all of this in MATLAB as well. There's a place in code here where I've obtained the two derivatives f df dx and df dy. So f is the function defining this surface. It's this function, it's the sine of x times y. Okay. So we can determine here the alpha, which is going to be this function fx evaluated at the a and b. So I think a and b stand for, yeah, a and b are the coordinates of the base point. And I can do beta is fy minus ab, f the y derivative evaluated at ab. And I could get the gamma then. So looking at the equation in the notes, the gamma was the original function f evaluated at ab. And then what was it? It was minus alpha times xp. So xp is a, the x coordinate of the base point, and then minus beta, beta times b. So that alpha, beta, and gamma there should be the coordinate, the coefficients in that equation z equals alpha x plus beta y plus gamma for the tangent plane. So that command there is where the surface is shown along with the two slice curves. So if I get all of that code just appearing before it, so the tangent plane will be a plot 3D. So MATLAB has equivalent commands for plotting three-dimensional functions. So we're going to have alpha times x plus beta times y plus gamma and these have this construction here for setting the x and y coordinates. The extent in the x and y directions of the two coordinates for the plot. And I'm going to make you can have this opacity, and again MATLAB will have similar constructions to make the tangent plane a little bit transparent so we can see through it. I'll make it a different color. Okay. So then I add on to the plot here, as well as showing the surface. In that show command, the surface was P, and X slice and Y slice are the two cross sections, and so we'll try and put in the tangent plane as well. So I might get a few error messages here. Okay, this is something of a miracle for anything to work first time like that. So there's our surface, the surface in blue, and the green tangent plane. Again, we're at the origin here. This surface has got zero slope in both directions, so it's not particularly interesting. But if we move the base point off the origin slightly, so there's our surface. We can still see the two cross-sectional curves. So when you can experiment around with this little widget yourselves, I'll put the link to it on the after the lecture recording. Experiment around with different base points, and you can appreciate there how the surface is the same tangent as the tangent plane in the two directions. When I line it up like that, you can just about see that the green cross-sectional curve is going left to right across the page here. And it's sloping upwards at about 45 degrees at the base point. You can just see the base point there just below the mouse hand. So you can see there that the tangent plane is indeed, let me just confirm it all fits together, has the same slope as the cross-sectional curve there at the base point. If you spin it around to look, see the red one is just going in and out of the page. You can't really see the red cross-sectional curve. But you spin it around so that you can. Looking at it from that direction, you can kind of confirm that you see the slope of the tangent plane from left to right now, looking at it from this side, does agree with the slope of the red cross-sectional curve at the base point as well. Okay. So I'll put the link to this in the comment to the video, and it's certainly something you could try and reconstruct in MATLAB as well, or indeed take the Sage code that I've got here and mess around with it further. Let's just see if we can confirm our the example we just worked on, example 1.5. Because we should just be able to go in and change the definition of the function up here, so rather than sine of x times y, we can confirm this. This is x squared times y. X squared times y plus 2 times y squared plus x plus 1. I'm just worried about these. So the base point was 2, 3. So let's just go a little bit either side of 2 and 3. So I'll make the x limit 4, so I'll go plus and minus 4. Let's make the y limit 4 as well. I think that's all we have to do. Yeah, I was afraid of this. Okay, so this function is, it's starting off at low values, but it's then getting extremely extremely tall. So that's what's doing it there. I'll try and zoom it in a bit on the base point 2, 3. Just go a equals 2. It's going to be a bit hard. Try it here. Still hard to see. The difficulty with this visualization here is there's extreme differences between the function values at certain points, so it's just turning into an extremely tall, thin plot. Now there are commands we need to kind of force the plot to flatten out in that, but I won't try and discover those at this point. Okay, so we'll leave it there. Now just to remind you the things you've got in play, the things you can be working on. It's all of exercises 1.1 and also the extra problems sheet as well. We'll be finishing those off in the tutorial and getting help with any outstanding problems you have with those.